Okay, so we're now in the magic section of not just this chapter, but a few chapters. This is a big deal, and I'm afraid to even say it because I'm afraid it's going to sound like I'm just giving you a commercial. All right, so we're only going to have a couple questions that come particularly from this chapter, but if you can understand this chapter deeply, you're going to get a lot of what's upcoming. So I'll do my best to be clear and concise, and I ask you to please pay very close attention to what's going on here. It's very important. All right, so you remember now you had Markovnikov addition when you were doing hydrohalic acids bonding to a pi system. Remember that from section 9.3. And here's how it looked. You have pi electrons coming and attacking a hydrogen. And these bonding electrons going off to make a bromide. In its wake, you're left, and this was challenging then, right? Because you didn't know if the hydrogen was going to go here to this carbon or to this carbon, right? Was it going to make a tertiary carbocation or a primary carbocation? Well, you probably have memorized by now that it makes a tertiary carbocation, right? And so the hydrogen goes to the carbon that already has the most hydrogens on it, and it's because of the stability of the intermediate. Now that we've got that, the bromide comes in and attacks and makes a new bond. Okay, it attacks both from the top and the bottom because we have a trigonoplanar intermediate. Big deal. Right? It attacks both on the top and the bottom. But since we've got two methyl groups here, it doesn't matter which. And we say that that's not a chiral compound. All right, very cool. Now with a conjugated diene, we get two products. And let's look at why. So first of all, let's name these. This is 1-butene. This is 2-butene. This is 3-bromo. Excuse me, right? You see it? And this is 1-bromo. All right. So let's see why we get these two. This is very important. So first of all, if we're talking about butadiene, both these pi systems are the same, right? So both these pi bonds are the same. So let's just choose one of them and say we get attack these pi electrons to that hydrogen, which is exactly what you would expect. And then these electrons go off and make a bromide. Well, so this is what you're left with. You're left with more substituted carbocation. So the hydrogen goes on the carbon that already has the more hydrogens on it, right? And but now look at this. We now have an sp3 hybridized carbon in the end, that methyl carbon, and nobody's going to mess with it. But we still have 3 sp2s. Okay. Now, since there are 3 sp2 hybridized carbons, we have 3 unhybridized p orbitals, which I'm drawing as sticks, right? You know, your pictures oftentimes are drawn as sort of dumbbells or something like that, right? We've got side-to-side overlap, which we indicate by that double bond right there, but you're going to have some side-to-side overlap here too because this one's empty. So there's no reason not to have some side-to-side overlap over here too. Look at that. And that's exactly what happens. What we get is resonance, right? Now, it turns out this is not an equilibrium. Be very careful. This is a resonance, and what that means is that the real structure is some combination of these two, which we sometimes draw like that, right? We have a partial positive here on this end, partial positive here on that end. You see that? This carbon right here has it has a resonance hybrid that's got a positive charge. This one has got a resonance hybrid, a resonance contributor that's got a positive charge. These two, carbons 3 and 1. So it's positive 1 over here and neutral over here, and that makes it partial positive. This one is neutral over here and partial positive over here, which makes it partial positive, right? So you know now the bromide is going to attack either here or here, right? So what intermediate would result if the hydrogen were added to any of the other carbons in the molecule? Okay, that's a good thought question. I'm going to stick with this story right now. Okay, with this story, you're going to get bromide attack at the 1 and the 3. Let me go back one slide for a second. It's exactly what happened. Look at that. Boom. Beautiful. Okay, so given the whole story now in one picture. Boom. Boom. Resonance hybrid. This is all one thing now, don't forget. This is not an equilibrium. This is a resonance. Okay? So you've got some positive character here and some positive character here. Right? And they're depicted by showing these two resonance contributors. Now the bromide comes in one story and adds here. And this is called 1,2 addition because here was the one bond, or one carbon, and here's the 2 carbon. So it's called 1,2 addition. All right? And this was the one, if this is the 1 carbon, right? 2, 3, 4, this would be 1 because the hydrogen goes here. 4 addition. 1,4 addition is there, right? There's the 1 hydrogen and the 2. 1,2 addition or 1,4 addition. This is called the 1,2 adduct, and this is called, as you can see, the 1,4 adduct. All right, so the resonance stabilized carbocation can be attacked by the halide. I've just said this now from either side. At either site that is sharing the positive charge. How is 1,2 addition different from 1,4 addition? I encourage you to stop the video now and write out a couple sentences about this. How is 1,2 addition different from 1,4 addition? Stop the video, write out a couple sentences. If it doesn't make sense, go back and look at the last couple slides. Practice with Skill Builder 17.1 now. Okay, so the addition of bromine to diene also gives 1,2 and 1,4 addition for the same reason, right? It's almost identical mechanism from before. All right, very similar. So you have a BR, you've seen this before. Boom, boom. And I'm not going to draw your intermediates, but you should. You should pause the video right here and draw out the intermediates. Draw out the whole mechanism for that. Super practice, very important. Okay, now finally, predict the major products for the reaction below and do that with a mechanism. Okay, predict the major products for the reaction below and do that with the mechanism and show all the stereochemistry.